So, welcome to the lecture series on mathematical methods and applications. So, this is the last lecture on Laplace transforms. We have seen so many things on Laplace transform, so many applications. Now, this is basically solution of partial differential equations using Laplace transform, that how Laplace transform is useful for solving partial differential equations. So, let a partial differential equation along with initial and boundary condition is given to us. Let a solution of such a partial differential equation be u x t, okay, u x t, two independent variables are involved, x and t. To find u x t, that is a solution of this partial differential equation using Laplace transforms, we take Laplace transform with respect to one of the variable, one of the independent variables, say t. For partial derivative with respect to the other independent variables, we assume that the operations of differentiation and integration of Laplace transforms can be interchanged. So, this we assume that with respect to the other independent variable, the operations of differentiation and integrations can be interchanged. Now, let us see, suppose you have u x t, which is a function of u x t, it is a function of two independent variables x and t. Now, suppose you take partial derivative with respect to x and let us compute the Laplace transform of this, okay, Laplace transform of del by del x of u x t. So, what it is? By the definition 0 to infinity del by del x of u x t into e की power minus p t dt. Because we are taking Laplace transform with respect to the independent variable t. So, that is why we are taking t here, because we are taking Laplace transform with respect to the independent variable t. So, this we can write like this, it is equal to basically this can be taken out. So, it is del by del x of integration 0 to infinity u x t, because this integration is with respect to t. So, del by del x can be taken out. So, e की power minus p t dt, and this expression is nothing but Laplace transform of u x t. So, suppose Laplace transform of u x t is suppose u x p, it is again a function of two variable, x is there and we are taking Laplace transform with respect to t, in place of t we will be having p. So, this will be nothing but, this is nothing but u x p, Laplace transform of u x t, small u x t, and it is del by del x, we can write d by dx because p is a parameter. So, this can be written as del by del, Laplace transform of del by del x of u x t can be written as d by dx of capital U x p, where capital U is nothing but Laplace transform of small u with respect to t. Now, similarly, if we find second partial derivative of u and take the Laplace transform of this, so this is nothing but d square by dx square of u x p. This can be derived on the same lines. Now, let us compute Laplace of partial derivative of u with respect to t. What is this? So, this we can easily see, because so Laplace transform of del by del t of u x t. So, we know that Laplace transform of f dash t is nothing but p f p minus f 0, where this f p is nothing but Laplace transform of f t and this f 0. Okay. So, in the same way, this can be written as, we treat x as constant term. So, this can be written as p into Laplace transform of u x t, which we are taking as u x p minus u x 0. Okay. This can be written as this way, because x we are taking as constant, we are taking Laplace with respect to variable t. Okay. Again, if suppose you want to find out second order derivative of this term of u x t, so again by the same concept we can write it is p square u x p minus p into u x 0 minus u dash. So, dash derivative with respect to the variable for which Laplace transform is to be we have taken. Okay. So, here we have taken Laplace transform with respect to t. So, derivative with respect to t only, so that is u t x t x 0. Okay. Because when we take Laplace transform of second derivative of f, it is nothing but p square f p minus p f 0 minus f dash 0, and derivative is with respect to t. So, here also the partial derivative with respect to t only. Okay. Now, let us solve this problem using Laplace transforms, this simple problem. Now, what this problem is? It is del u by del t plus x del u by, it is del u by del x, sorry, del u by del x plus x del u by del t is equals to 0. U at x comma 0 is 1, these are the initial conditions, and u 0 t is equals to 0, this is given to us. So, this is some first order partial differential equation and we want to solve it. So, let us solve this problem using Laplace transforms. So, you take Laplace transform both the sides. So, now we are taking Laplace transform with respect to t, independent variable t. So, this can be written as d by dx of Laplace transform of this, which we are taking as u x p plus x t test constant, and del u by del t is nothing but p into u x p minus u x 0 is equals to Laplace transform 0 is 0. So, here Laplace transform of u x t I am taking as u x p. Okay. Now, this is nothing but it is du by dx, this capital U is this, I am taking like this. So, plus x into p capital U, and u x 0 is 1. So, when you substitute 1 here and this will go to right hand side, this is nothing but equal to x. So, this is simple first order linear differential equation. The first order linear, basically when you take Laplace transform in any PD, okay. So, this will give a ordinary differential equation. You use your usual techniques to solve this equation and then take Laplace inverse to find out the solution of the given PD. Okay. Now, how to find the solution of this? First you find integrating factor. So, what is integrating factor? E ki power integral x p dx. So, this is nothing but e ki power p x square by 2. Okay. And the solution will be nothing but e ki power p x square by 2 into u is equals to integral right hand side into integrating factor dx plus integrating constant c. Now, of course, this is basically a function of p, because here two variables are involved, p and x. P is an arbitrary variable, arbitrary constant we can say, and x is a variable. It will be we are integrating with respect to x, so it will be some function of p. Now, how we will integrate this? We can take this as say t. So, p x square by 2 we can take as t. So, it is p x dx will be nothing but dt. So, this is equal to 1 by p integral e ki power t dt plus cp, and it is 1 by p integral of e ki power t is e ki power t itself, and t is nothing but p x square by 2. So, e ki power p p x square upon 2 plus C p e की power x square by 2 into p into u in the left hand side. So, what we obtained, u is equal to 1 by p plus C p into e की power minus p x square by 2. Now, to calculate C p, we will use the second condition u 0 to e is equals to t. Okay. Now, suppose it is 1, what is u x p? U x p is nothing but Laplace transform of u x t, which is nothing but 0 to infinity u x t into e की power minus p t dt. Now, when you take x equal to 0, so here x equal to 0 and here also x equal to 0. So, u 0 p will nothing but a Laplace transform of u 0 t, and that is nothing but Laplace transform of t, because u 0 t is nothing but t. So, this is nothing but 1 by p square. Now, when you apply this condition here, okay, so it is when you take x equal to 0, put x equal to 0. So, u x 0 is nothing, u 0 p is nothing but 1 by p square. So, 1 by p square equal to 1 by p plus C p into 1. So, this implies C p is nothing but 1 by p square minus 1 by p. So, therefore, u x p is nothing but, therefore, u x p is nothing but 1 by p plus 1 by p square minus 1 by p into e की power minus p x square upon 2. Now, u x t will be nothing but Laplace inverse of u x p. So, it is Laplace inverse of this expression. So, Laplace inverse of 1 by p is 1 plus. Now, we have to find out Laplace inverse of 1 by p square e की power minus p x square upon 2 and minus Laplace inverse of e की power minus p x square upon 2 by p. Now, this x is here is not a variable, because we are taking Laplace respect to t. So, this x is not a variable, we are taking it as a constant to find out Laplace inverse, only p is a parameter. So, we know this, we know our result that Laplace transform of f t minus a into u t minus a, where u is the unit step function at t equal to a, is nothing but e की power minus a p into f p, where f p is nothing but Laplace transform of f t. Okay. Now, this one will remain as it is plus. Now, the Laplace inverse of this is t, 1 by p square, Laplace inverse is t, e की power minus as, a is x square by 2. If you compare with this, so a is nothing but x square by 2. Okay. So, and Laplace inverse of this is t, so f t is t. So, the Laplace inverse of this entire expression by this formula is nothing but t minus x square by 2, because a is x square by 2, and u of t minus x square upon 2 plus minus. Okay. Now, here Laplace inverse of 1 by p is 1, so f t is 1 and a is x square by 2. So, again this expression will give u t minus x square upon 2. So, therefore, the final answer is 1 plus t minus x square upon 2 minus 1 u of t minus x square upon 2. So, this will be the solution of this differential equation. We can use this property to simplify this expression. So, the variable under which we have taken the Laplace transform, take only that variable as a variable, other variables take as a constant, take other variables as constant. Okay. So, this is how we can simplify this PDE. Now, let us solve a second order PDE. So, these are the applications of Laplace transforms. It cannot not only solve ODE or integral equations, it may solve PDE also, as we have seen in these examples. So, what is the second order equation? UTT is equals to UXX, and 0 is less than x less than L, and t greater than 0. Conditions are given to you. What are the conditions we will use when we apply Laplace transform both the sides? So, take Laplace transform both the sides. Okay. So, what will be the Laplace transform of del square u by del t square? It will be nothing but p square into u x p minus p u x 0 minus u t x 0, because we are applying Laplace transform with respect to t. So, this is equal to, this is nothing but d square upon dx square of u or uxp, where uxp is nothing but Laplace transform of uxt. Now, this is p square uxp minus, now ux 0 is 0 given to us. So, p into 0 minus, and ut 0 is nothing but sin pi x by L. So, it is sin pi x by L given to us, and this is nothing but d2 u upon dx2. So, this implies d2 u upon dx2 minus p square u is nothing but minus sin pi x by L. Okay. So, it is a second order linear differential equation. So, we can find the solution of this equation. First we find complementary function or complementary solution, then we find particular integral, and the sum of these two will give the complete solution of this differential equation. So, what is the complementary equation here? So, it is nothing but d square minus p square times u is equals to minus sin pi x by L. So, complementary function will be nothing but it is m square minus p square equal to 0. So, m will be nothing but plus minus p. So, complementary function will be nothing but a. Now, it will be a and b, which are the arbitrary constants, are nothing but function of p here, because we have two, because u contains two variables x and p. Okay. So, ap e ki power p x plus bp e ki power minus p x. Okay. Now, for a particular integral, it is nothing but 1 upon d square minus p square of minus sin pi x by L. So, you simply replace d square by minus a square, and a is nothing but pi by L. So, this is equal to 1 upon minus pi by L whole square minus p square, and it is minus sin pi x by L. So, this is nothing but sin pi x by L upon pi square upon L square plus p square. So, this will be pi. So, what will be the complete solution, that is capital U. So, capital U x p will be nothing but Cf plus pi. So, Cf is nothing but ap e ki power p x plus bp e ki power minus p x plus pi, which is sin pi x upon L upon p square plus pi square upon L square. So, that will be the complete solution of this differential equation. Now we will use the other conditions given to us to calculate AP and BP. To calculate these functions, we will use the other conditions. Now what are the other conditions? Okay. Now now u 0 t is equal to 0. Now u x p is nothing but Laplace transform of u x t. So u 0 p will be nothing but Laplace transform of u 0 t, which is nothing but 0 because this is 0. And other condition is u L t equal to 0. So you substitute x equal to L here. First we substitute x equal to 0. When you substitute x equal to 0, so u 0 t is 0. So Laplace of 0 is 0. Now you substitute x equal to L here. So u L p will be nothing but Laplace transform of u L t, and u L t is again given as 0. So it is again 0. Now apply both these conditions, both this condition and this condition in this equation to calculate A and B. Okay. Now you substitute x as in this equation, you substitute first x as 0. So put x equal to 0. When you put x equal to 0 here, so the left hand side is nothing but 0. 0 is equal to e ki power 0 is 1, it is AP, plus this is nothing but plus BP, and sin 0 is 0, so it will be 0. Okay. So this is one condition. Now put x equal to L here. When you put x equal to L, so u capital U L p is again 0. So when you put x equal to L, so it is 0 is equals to AP e ki power p L plus BP e ki power minus p L, and at x equal to L sin pi, which is 0. Okay. Now these are the two equations in two unknowns A and B, capital A and capital B. If you take the determinant, so these are two equations. Okay, AP plus BP is equal to 0, and AP e ki power PL plus BP e ki power minus EPL is equals to 0. If you take a determinant of 1 e ki power PL and e ki power minus PL, so it is equals to e ki power minus PL and minus e ki power PL, okay, which is not equal to 0 for all P. So this implies this will be having a unique solution, and the unique solution in homogeneous equations where right hand side is 0 is nothing but the trivial solution, that is AP is equals to BP is equals to 0. Because the coefficient determinant or coefficient matrix, the determinant of data is equal to 0 is not equal to 0. So not equal to 0 means unique solution, and the only unique solution is trivial solution, that is AP equal to BP equal to 0. So when you substitute AP equal to BP equal to 0, what we will obtain? So what will be UXP now? UXP will be nothing but AP and BP are 0, so it is nothing but sin pi x by L upon p square plus pi square upon L square, and uxt is nothing but Laplace inverse of uxp, which is equals to, now you want to take Laplace inverse of this equation, this expression. So sin pi x by L will come outside because it is free from t, it is free from t and p, it is free from p, sorry, okay. And this, for this Laplace inverse of 1 upon this, you divide and multiply by pi by L, so 1 upon pi by L into Laplace inverse of this is sin pi by L pi upon L into t. So, the final answer is L upon pi sin pi x by L into sin pi t by L. So, this will be the final solution of this equation. So, similarly the questions based on PD can be solved using Laplace transforms. Okay. So, thank you very much.